Now that we've established exponentiation, we need to consider the inverse of exponentiation. We call the inverse of exponentiation the logarithm. In general, you have an input n, a function which raises a given base to the variable n, and an output k, which is equal to base to the power of n. For the logarithm system, k goes into a function, log sub base, operating on the input k. If k is equal to base to the power of n, then the output will be n. Let's consider a slightly less general example. Let the base be 2. Consider an input n, a function 2 to the n, and an output 2 to the n. To drive the system backwards, we need to put 2 to the n in and have n come out. We write this function as log base 2 of 2 to the n. For a specific example, let the base equal 2 and n equal 3. So 2 to the 3 is 8. Then log base 2 of 8 is 3. With some practice, there are certain logarithms you can do by inspection, especially if the argument of the logarithm is an exponential function with the same base as the logarithm. There are two rules you must remember to guide the use of logarithms. I'm going to state them here. I suggest attempting the derivations of these rules on your own. They follow naturally from the rules of exponents. Log base b of a to the n is equal to n times log base b of a. This is known as the power rule. Log base b of x times y is equal to log base b of x plus log base b of y. This is known as the product rule. We will be making use of logarithms by exploiting its definition as an inverse function in equations. For instance, let's say 2 to the n is equal to 2 times x. To solve for n, take the log base 2 of each side. Log base 2 of 2 to the n is equal to log base 2 of 2x, which simplifies to n equals log base 2 of 2 plus log base 2 of x, which again simplifies to n equals 1 plus log base 2 of x. The general term logarithm can have any base, but we will mostly be concerned with the natural logarithm, which is the base e. We denote the natural logarithm by ln bracket argument, close the bracket.